For nearly a century, cosmology has described a universe born in fire, expanding through space and time, dominated by unseen components. The Lambda CDM model has been extraordinarily successful, but every model rests on assumptions. What if cosmic redshift has another origin? What if time itself is not what we think it is? This is the exochronous universe, rethinking cosmology from first principles. For nearly a century, cosmology has been guided by a remarkably successful idea: that the universe began in a hot, dense state and has been expanding ever since. Today, that framework is known as the Lambda Cold Dark Matter model, or Lambda CDM. It is often described as the standard model of cosmology, our best working description of how the universe began, evolved, and acquired its large-scale structure. But as new telescopes probe deeper into space and further back in time, some cracks may be beginning to show. Is Lambda CDM still the right model? Or is it time to consider something more radical? The Lambda CDM model rests on three main pillars. First, cosmic expansion. In the 1920s, Edwin Hubble discovered that distant galaxies are receding from us, with velocity proportional to their distance. This relationship, now called Hubble's law, implies that space itself is expanding. Extrapolate backwards, and the universe becomes hotter and denser. Second, the cosmic microwave background. Arno Penzias and Robert Wilson accidentally discovered this faint microwave glow in 1965, relic radiation from about 380,000 years after the Big Bang, when atoms first formed and light could travel freely. These tiny fluctuations, 1 part in 100,000, encode a wealth of information about the universe's composition and geometry. Third, structure formation. Under gravity, small density fluctuations grow into galaxies, clusters, and the vast cosmic web. To explain how structure forms as rapidly as observed, Lambda CDM proposes that most matter in the universe is not ordinary atoms, but cold dark matter, invisible, non-interacting mass detectable only through gravity. And to explain why cosmic expansion is accelerating today, the model includes lambda, representing dark energy, a mysterious form of energy permeating space. Put the pieces together and we arrive at a universe composed of 5% ordinary matter, 27% dark matter, 68% dark energy. LAM-CDM is not just elegant, it is extraordinarily successful. It predicts the detailed statistical pattern of fluctuations in the cosmic microwave background with astonishing precision. It explains the relative abundances of light elements, hydrogen, helium, deuterium, produced in the first few minutes of cosmic history. It accounts for gravitational lensing, galaxy clustering, and the large-scale structure of the universe over billions of light years. Simulations based on Lambda CDM reproduce the filamentary cosmic web seen in deep surveys. For decades, the agreement between theory and observation has been so precise that cosmology entered what some called a precision era. But precision cuts both ways. In recent years, several observations have raised uncomfortable questions. One of the most discussed is the Hubble tension. Measurements of the present-day expansion rate using nearby supernovae give a higher value than predictions derived from the early universe CMB data. The discrepancy is small, about 5 to 10%, but statistically significant. If both measurements are correct, something in the model may be incomplete. Then came the launch of the James Webb Space Telescope. JWST has revealed surprisingly massive and apparently mature galaxies at very high redshifts, meaning they formed extremely early in cosmic history. Some appear larger, brighter, and more chemically evolved than expected under standard structure formation timelines. Are these objects statistical outliers, or signs that galaxies assembled faster than Lambda CDM predicts? There are also smaller-scale puzzles. The core cusp problem in dwarf galaxies, the missing satellites problem, the distribution of satellite galaxies around larger hosts. Individually, none of these necessarily falsifies Lambda CDM, but collectively they prompt discussion. It is important to be clear. Lambda CDM has not been overthrown. Many of these tensions may ultimately be resolved through improved astrophysical modelling, better understanding of star formation, feedback, dust, or observational biases. History shows that cosmology is resilient. Yet science advances not only by defending successful models, but by questioning their assumptions. Dark matter has never been directly detected. Dark energy remains unexplained, and some of the newest observations appear to push the model to its limits. For nearly 100 years, the hot Big Bang paradigm has guided our understanding of the universe. It remains one of the most successful scientific theories ever constructed. But as our observational reach expands, so too must our willingness to re-examine foundational ideas. So we are left with a profound question. Is it time to consider an alternative cosmological paradigm? In this series, we will examine the foundations of modern cosmology in detail. We will explore the origin of matter itself, the formation of the cosmic microwave background, the large-scale structure of the universe, and the physical origin of cosmic redshift. These observations form the pillars of modern cosmology. But we will also ask a deeper question. Could these phenomena be explained within a simpler cosmological framework, one that does not require inflation, dark matter, or dark energy? In the coming episodes, we will explore that possibility.